Hello and good afternoon, everybody. Today we're going to talk a little bit about some organic reactions, certain things that only happen when we're looking at organic chains or trying to add functional groups or remove functional groups. We're going to look at 7 simple examples, and what we're really going to focus on here is definition and like places where this happens. Right. So, first, the two that I want to focus on first are substitution and addition. Right, these are paired in a nice way. Substitution is a replacement of one atom or one group on a carbon chain with another atom or group on the chain. So what we'll see here in this example is we will see propane plus chlorine and what's going to happen here is that one of these chlorines is going to replace one of the H's that is currently on this propane. If you go on to AP or college level chem, they'll talk about how you can tell which of the bunch is going to get replaced. But here all we're really focusing on, again, like I said, is definition and some common example. So we're actually going to see one of the chlorines kind of trade with the H's. Can I speak words? We're actually just going to see a kind of trade where one of these H's is going to swap with one of these chlorines. They're going to substitute out one for the other and just swap their position. Right? It is a substitution like in any sports match. Right? When we trade out one player for the next, here we're just going to trade out one H for a Cl. We could trade out an H for a branch. We can have that as a substitution. We can trade an H for a different halogen. We can trade it for an oxygen. We can trade it for an OH. It's not specifically for chlorine. That's just the example that we have here to look at. Right. And this, the interesting thing to note is that this only happens in alkanes. It only happens in carbon chains where the carbons are all single bonded together. And the reason for that is actually directly connected to the next one we're going to look at, which is an addition. Right? If we look at an addition, this is only in alkenes or alkynes, so it needs a double or a triple bond. And the reasoning here is that it's going to add an atom or a group at the double or triple bond. So we're going to see a little bit of a different setup here. We're going to draw one propene. I'm going to try to stick to black with all of the bonds here, so just bear with me a second. So we're going to have I have too many bonds already, so that goes away. And there. So we're going to have one propene. We're going to have that interact with a chlorine molecule, just like before. I'm going to make our chlorines a little bit of an easier color. Let's make them green. And for a addition, we're not swapping, right? It's not a substitution. We're not going to swap. Instead, what we're going to see is actually that they're just going to add themselves at the double bond. So the two chlorines are going to cause the double bond to break, crack open, and make room for both chlorines to get added on. Right, so this bond here is going to break, and when that bond breaks, it means that there's more room for things to add on, right? There's an empty spot here and an empty spot here, and those chlorines can break apart from each other and attach themselves to those open spots. Right, and this can happen at a double bond or a triple bond. If it would happen at a triple bond, we would just have a double bond remaining with the pieces added, replacing the third bond, right, replacing the triple. Right, so these two go hand in hand, substitution and addition. It's all about putting more stuff onto the chain, right, adding to the carbon chain. Here, with addition, it is a total, globbing more things on, like we see with this example. Whereas with substitution, like we saw before, it's a replacement. Right here, this H and this Cl are going to swap, so replacing one with the other, putting different stuff onto the chain. The third reaction that we're going to look at is a fermentation. And here we're not even really gonna break this down. Is one where really all we care about here is the definition. A fermentation is a process that makes an alcohol. Right. We've talked about this a lot in previous classes. If you've taken living environment, you talk a lot about fermentation. It's what we do in our mussels. We have lactic acid fermentation, alcoholic fermentation. Right, we've got these processes that are going to break sugars down into alcohols and carbon dioxide. Right, we see this happening in plants. We take advantage of this when we want to make. We as humans want to make alcoholic beverages. Right, if you go to a winery, a brewery, a distillery, that's all fermentation that they're taking advantage of, but they're harvesting out the alcohol to then bottle and sell. Right, but the idea here is we're breaking sugars to make alcohols. It's champagne is specifically bubbly because of the way that they then package it. Alcohol on its own is not bubbly, right? Like a bottle of liquor is not a bubbly carbonated thing. But when you have things like beers, when you have things like champagne, that's added CO2, right? So they create it, they make alcohol and CO2, they keep just the alcohol, and then later when they do the actual bottling of the substance, they'll put back carbon dioxide. But if you've ever bought like unpasteurized apple cider or unpasteurized juice of any kind, right? Any fruit juice, the sugars in that fruit juice will ferment over time. So if you ever had just an older bottle of juice, you have that release of gas. That release of gas is caused by the fermentation process. The fact that there's CO2 being made in this bottle as your really old orange juice or really old apple juice ferments. right? So for fermentation, it's really a definition thing. We're trying to connect the idea that fermentation is breaking a sugar to make alcohol and CO2, right? Kind of a refresher from living environment. You might see more of this if you move on and do any AP environmental, right? But that's what we're looking at here. Our fourth reaction is a very familiar reaction to us. It's the idea of combustion, right? And here now we get to put the right word in here, right? It's the reaction of a hydrocarbon with oxygen to make water and CO2. It's taking some small carbon chains or some large carbon chains, reacting them with oxygen to make a number of CO2 and water. Right? We've seen this reaction before, right? We've learned this pattern, but we didn't have the word hydrocarbon to put with it. This is, right, a combustion reaction is an organic reaction, even though it is not a new reaction for us. All right, moving forward, we have three more that we're gonna take a look at. The next two are paired together. Esterification makes an ester, right? It's got the name right there in it, right? Esterification, right? It's the idea of making an ester from an acid, right? An organic acid and an alcohol. And the reason it's paired with saponification is that these two are exact opposites. Right, esterification makes an ester from an organic acid and an alcohol. Saponification makes an alcohol and an organic acid from an ester. Right, so what we'll see here, if I can draw correctly, I'm just gonna put a double arrow and we'll see how this totally works both ways. Right here we've got propanol and butanoic acid, and when these two combine, we can take away that H and OH, which I'm going to put here in blue. And we're left with no, hey, whoa, watch out. What we end up is making an ester by the removal of H2O, right? These come away, these two pieces then attach. So I'm gonna label, right? This here becomes this here, right? And it attaches on where there's a spot now from removing the H and the OH, removing those little pieces that we then use to make a water molecule. And if I look at this process in reverse, if I add water to break this apart, I'm going to get my alcohol and organic acid back, right? Making esterification and saponification exact opposites. Right? One makes the ester, the other breaks the ester. me draw this out a little bit nicer for us. Right. Let's ignore this bit for right now. And draw this forwards and backwards again, just a little bit nicer so that we can see these pieces in color. No. And so here again we have our propanol and our butanoic acid, our organic acid and our alcohol. And what's going to happen is that when we redraw our pieces here, why does the propane attach to the right side instead of the left? Oh, that's just the way I have it drawn. I could flip this whole thing actually, and it won't make a difference. Right, if I did this instead, it's actually the same. Might make it a little bit easier to follow actually, so let's do that. Give me back my purple. Draw my O and my O and my blue H. Right, flipping the molecule isn't actually going to have any effect on it. It's still butanoic acid facing left or facing right. I just have a habit of putting the organic acid functional group on the right side, drawing from left to right. But it doesn't actually make a difference. So when I then attach these pieces, I'll go back to my red and I'll put my 3 carbons. I'll go back to my purple and I'll put my oxygen and then my 4 carbons and my other oxygen. I'll use black to fill in all of those bonds. And the only piece that's really changed at this point is now I have that separate from the rest. All right, I've got propyl butanoate and water. And if I look at this backwards, an ester plus water is going to make an alcohol and an organic acid. This is a reversible thing. Depending on the conditions, I can make this go forward or backward, right? Esterification, saponification being equal but opposite. The last of our 7 organic reactions that we're going to take a look at here is a polymerization. And really what this is another... oh, wait a second, going back. Why does the propane attach to the right side of the O instead of the left in the ester. Again, so okay, for that, when we're naming an ester, right, the name of this ester, the part that contains the O8 is the part that has the double bond O. So here, this has to be the 4 carbons because it's butanoate, so the double bond O has to go here. And then the propyl is the branch off of the O. And that comes from just the way we name esters. There is no spot to put this group anywhere else. It's replacing this H that was attached there. All right, so this piece, right, this OH and this H are gonna leave, leaving a bond here that can attach onto stuff, leaving a bond here that can attach onto stuff, and when they leave, those 2 bonds are just gonna attach together here to make the bond that then makes this an ester. Our last organic reaction is a polymerization, which is another kind of throwback from living environment. The idea that you can take a bunch of small pieces and connect them together to make a bigger thing. When we're talking about making a protein and connecting a number of amino acids together, that's polymerization. If you're talking about making a chain, you want to make this chain, that's polymerization, taking a bunch of identical or very similar small pieces to make a bigger piece. So that's our starches made from simple sugars. That's our amino acids making proteins. All right, many simple sugars. 1 starch. We could have many amino acids making 1 protein. We could have many nucleotides making 1 DNA strand. Right, the idea that you take a bunch of smaller things to make 1 larger thing. Right, a direct callback to living environment, but that is an organic reaction because all of these things, all of these molecules are organic molecules, connecting backwards to other things. So those are our 7 basic organic reactions. Addition and substitution, the first ones we looked at being the ones that we need to be able to actually look at and understand and identify. Combustion, something that we're already used to. Fermentation, a definition question. Polymerization, a definition question. Esterification and saponification, equal but opposite, either making an ester or breaking an ester. And the one that makes an ester has ester in the name. Going to go ahead and transition us into tutoring and office hours. And I will see you all later. Have a fantastic day, everybody.